Okay, so this video is the first half of section 1.7 in your Pre-Calc 1 text, and it is on domain. So what is domain? So domain, I like to think of it as a set of all possible inputs. And if we have a set of ordered pairs as the domain of that set is going to be all of the x values. If we have a function, f of x, and we just have an equation for it, the domain of the function is the largest set of real numbers for which the value f of x is a real number. So this is the quote from your textbook, but pretty much it's the values of x that make f of x a valid function. Okay, so often we are looking for values of x that don't give a real number of f of x. So, and then looking to exclude those from the domains. So let's take a look at what we mean by that. So there's a couple different types of functions that you'll see a lot of examples of in your text. And we have polynomials. So if we're looking at polynomials, we want to know what values of x can we compute a value of f of x. And so for these, there's actually really like no restriction on the domain. We can plug in any value of x and we can compute a value of f of x. Some numbers might be easier to compute that value, but we can still always compute a value of f of x. So there's no limitations on our domain. This is all real numbers. And when we write that in interval notation, that's mostly what your book is asking you to do. We write that in interval notation. We're going to start all the way at negative infinity and go to infinity. So this is all real numbers. This will be the same domain for all polynomial functions. All polynomial functions will have the same domain of negative infinity to infinity. Okay. The other type of example that we'd like to look at is rational functions. Rational functions, our denominator cannot equal 0. Dividing by 0 is undefined. We can't do it. So we want to find the value for x that makes the denominator equal to 0. We want to exclude that from our domain. So in this function, we have f of x plus x squared divided by x minus 1. We want to find any place where our domain is x minus 1 is equal to 0. So x minus 1 equals 0. Well, that's going to be, we add 1 to both sides, we get x equals 1. So we want to exclude that x equals 1 from our domain. The way we do that is we can go all the way from negative infinity all the way up to 1. We don't want to include 1, so we do these rounded brackets. These rounded brackets mean all the way up to but not including. And then we want to exclude 1, so we want to go start just after 1 and go all the way to infinity. So when we're excluding a number, this is the way we write it in interval notation. We wanted to exclude 1. So usually this is, we need to find where this does not equal 0. So we excluded 1 from our domain in interval notation. I apologize. This should be f of x equals the square root. So if we have a radical function, or if we have an even root, we can't take the square root of a negative number. So this 5x minus 15, whatever expression is underneath our radical sign, we have to say that's greater than or equal to 0. This has to be greater than or equal to 0. Okay, so we can add 15 to both sides. We're going to just solve this inequality for x. We get 5x is greater than or equal to 15. Divide by 5. We get x is greater than or equal to 3. Okay, so again, we took this expression that was underneath our radical. We said that's greater than or equal to 0, and then we solve that for x to find the values of x that give this function a real number, or it allows f of x to be a real number. Okay, so x has to be greater than or equal to 3. So we need to, in interval notation, we need to start at 3, and we can include 3. When we do these square brackets, we include that number, and we can go all the way, anything that's bigger than 3, all the way to infinity. Okay. Polynomials, just review. Polynomials has a domain of negative infinity to infinity. Rational functions, we have to find the value that makes the denominator, or we have to exclude the value that makes the denominator equal to 0. radical functions, this expression underneath our radical has to be greater than or equal to 0, and then we can solve for x. So the other thing that they'll ask you to do in this section is algebra with functions. We can take the sum of a function. So the function f plus g of x is f of x plus g of x. We're just adding those two together. We can take the difference, and again, we're just taking f of x minus g of x, and that gives us our f minus g of x. We can do the product. So f times g of x is just f of x times g of x. And we can do the quotient, which is f of x divided by g. F divided by g of x, again, is f of x divided by g of x. When we look at the domain of these, this quotient one, we can't have our denominator equal to 0. So this one, g of x, cannot equal to 0. So we need to find where g of x is equal to 0, and we need to exclude that. For all of the rest of these, and including the quotient, the domain of the domain of the function after we do the algebra is the domain of f, where it intersects the domain of g. So what that means is, like, if we're excluding something from f, we need, in the domain of the sum function, we have to just exclude everything that's excluded from the domain of f and everything that's excluded from the domain of g. And if we had something like in the domain, if the domain of f is x is greater than 3 and the domain of g is x is less than 10, well, then we have to have the function, the domain of the function after we do our algebra can only go from 3 to 10, because we have to exclude everything that's from both. But if it's a single number, it's easier to take a look at that way. So let's take a look at an example here. We have f of x is equal to x minus 5 and g of x is equal to x squared plus 1. So if we're going to do the sum function, we want to find f plus g of x. We're again going to be, this is equal to f of x plus g of x. So f of x is x minus 5 plus g of x plus x squared minus 2. Now we can combine like terms and reorganize this. This becomes x squared plus x minus 6, and this is our f plus g of x. Okay? The domain of this function, so we have where the domain of f intersects the domain of g. F of x is x plus 5. We can plug any value in for x. G of x is x squared minus 1. Again, as polynomial, we can plug in any value. So this domain of f plus g is just going to be all real numbers, negative infinity to infinity. It's a polynomial. Okay? If we want to take a look at f divided by g of x, again, this is f of x divided by g of x. So we plug those functions in. F of x is x minus 5. G of x is x squared minus 1. So this is our quotient function. To find the domain of this, again, it's the domain where where the domain of f intersects the domain of g. And what we said from the sum function is that that's all real numbers. But we also have to exclude where g of x is equal. We have to exclude where g of x is equal to 0. So our denominator here can't be equal to 0. And I'm going to rewrite this. This is x minus 5 divided by x squared minus 1 is a difference of squares, x minus 1 times x plus 1 minus 1. Okay, and then x minus 1 is equal to 0 when x equals 1. X plus 1 is equal to 0 when x is equal to negative 1. Okay. So now we have to exclude 1 and negative 1 from our domain. So we do that. We start at negative infinity. We go all the way to our first exclusion, which is negative 1. And we go from our first exclusion from negative 1 to our next exclusion, which is 1. And then we go from 1. We have no other exclusion, so we go all the way to infinity. Okay. So that is the first half of this section 1.7. There will be a second video on composite functions in their domain. The main lessons from this is the domain is any possible input that we can put into a function, or we look for exclusions. Polynomials, there are no exclusions. We go to negative infinity to infinity. Radical functions, the expression under the radical sign has to be greater than or equal to 0. And when we have a quotient, our denominator can't equal 0. Those are the main exclusions that we'll be looking for when we're evaluating domain.